So in this part of the inductive circuits, we are going to take and look at what the effects of putting an inductor and a resistor into a circuit. In this case, a series circuit. We'll talk about parallel later on. As we have studied already, that due to this sinusoidal waveform cutting across an inductor, which creates a magnetic field, we're going to get a counter EMF. Inductive reactance is the result of this counter EMF, and we measure that inductive reactance in ohms, which is 207.35. So this 207.35 ohms is a result of this AC signal, in which case is 5 volts and 1 kHz. Really has nothing to do with the 5 volts, but it does deal with the frequency. So because of this frequency right here, this inductor is approximately 207.34. The inductive reactance is equal to 207.35 ohms. So we can actually find the impedance of this circuit. And remember the impedance. Remember, we're dealing with a right triangle. So when we're dealing with a right triangle, we have to take and we're going to have to use some trigonometric functions. In this case, impedance Z total is equal to x sub L1 squared plus R1 squared. In this case, when we do all the math, we can obtain 230.20 ohms resistance. So the second part is we want to find I total. So I total is current total, and we know that current total throughout the series circuit is the same. In this case, we just take the 5 volts peak divided to 230.2 ohms. That is our impedance. So V total over impedance total, and that gives us 21.72 milliamps. And using Ohm's law, we can actually now find the voltage across R1 and X sub L1. In this case, we take the current total times it by R1. In this case, we get 2.17 volts peak R1. And X sub L1 is going to be equal to the current total, 21.72 milliamps, times that by 207.35 ohms, which is what we found up here. And that gives us 4.05 volts peak X sub L1. So at this point, we cannot just add these two values up because remember, we're dealing with a trigonometric function, sinusoidal waveform. So we have to use the Pythagorean theorem, parts of the Pythagorean theorem on here, in order to solve for V total, to check for V total on here. So the other way we could find voltage across VR1 and X sub L1 is using the voltage divider rule, and I'll just put that over here. The voltage divider rule, if we wanted to say find X sub L1 using the voltage divider rule, what we would do is take the X sub L1 over the impedance total, and then what we're going to do is multiply that by your V total. In this case, our voltage total is peak. And if we did that, you would get the same value here. So X sub L1 is going to be equal to 207.35 ohms divided by 230.20 ohms. And then you're going to do, remember your parentheses, times it by 5 volts peak. In this case, you get 4.5 volts X sub L1, which is the same as this part. So if you see that, you notice that these two values are exactly the same. So the second part of this problem is let's check to see if these two R1 and X sub L1, VR1 and X sub L1 do equal up to our source voltage. Again, we're dealing with the right triangle, Pythagorean theorem. And in that case, what we're going to do is, let me move everything up. So what we're going to do now is we're going to take and we're going to apply, here's the Pythagorean theorem triangle. So this is R1. Remember, R1 has no phase change. Vx sub L1 will have some sort of phase change. In this case, that's why it's pointing to the upward part of it. And we'll talk about that in a second. And then V total is wherever here. So this is the hypotenuse. That's the opposite, and that's the adjacent side. So if we take and we apply Pythagorean theorem, and we apply it, V total is equal to the square root of VR1 squared plus Vx sub L squared. And if we do all the math, it does indeed come up to be approximately 4.99 volts total. The reason why we're off is because of our decimals. We did not go out, we did not take out to significant figures on that. So finally, what we want to do is find the phase angle or the phase change between I and VT. In this case, I'm going to use the impedance here of the circuit. So if I take the impedance, that I'm looking for the phase angle using the impedances, I take the arctangent of x sub L over R. In this case, when I do that, I get 64.25 degrees. Remember, you have to be in degrees. If you're calculating radians, you're going to get a whole different answer. So that states that the 64.25, I lags VT by 64.25 degrees. And that is represented right down here. So the question you should be asking yourself is, could I find the phase angle change using anything else I've calculated? Right now I just used the resistances down here on it, but could I use my voltages and find the phase angle change? Yes, you can. Same thing, just have to keep your units the same. So you take 4.05 and divide it into 2.107, take the arctangent of those, and you will get 64.25 degrees. You will get it. Before I show you the circuit I built for the problem we just did, what I want to show you is what it actually looks like on the scope. So basically what I have here is channel 1, which is yellow, is my voltage total. My channel 2, which is blue, is my voltage across the inductor. The red is actually a math function, and what I did is I take the voltage total and I subtracted it off from the inductor. In this case, if you look at it, it comes out to be 2.16. It's bouncing a little bit, but it is 2.16. And let's see if I can get it a little better on there. It's about 2.16. So if you remember right, VR1 is 2.17. So that red is actually measuring the voltage across R1. Because we're taking L1, the voltage across X sub L1, and we're subtracting it off of voltage total, and we get R1. So this oscilloscope can do that trigonometric function for us very easily. So again, yellow is voltage total, blue is X sub L1 across our inductor, and then the red right here is actually the result of a voltage across our resistor, which is really neat. Now, if you also notice on here is that our phase change right here. So our phase change on here is the voltage from the blue and the yellow. So we could say that the inductor is leading, the inductor voltage is leading the voltage total by approximately some sort of degrees. And we'll see about that in a second here. Before I actually show you the circuit, what I want to show you is that this 23 to 24 degrees right here, that is our phase change from 2 to 1. So you're probably thinking, well, we calculated 64.25. Well, if you actually take 90, subtract it from 24, 23, you're going to come close to 64.25. So, and I'll explain that a little later on, why we have to do that math on here. But so let me show you the circuit that I built that displays this. So here's my circuit. I'm going to put this in. Again, I have an inductor and my resistor. And I could use the multimeter to come up with these values. And this would be an RMS value, but if I do, let me show you what that would look like. I'm going to move some stuff over here just to bring my meter in a little closer. So I'm going to put that on. Put the AC. I'm going to try to bring this over just a little bit more. Okay, so if we take a measurement across the resistor, and this will be an RMS value. So I get 1.4. So if I take 1.40 times it by 1.414, I get 1.97, and we calculated approximately, about 2.1, so close to 2 volts. Yeah, that's about close. So again, I'm going to get approximations. I'm not going out all of my decimals, but again, if I just wait and let it go up, yep, looks good. And then if I take and I put it on this one, I get 2.84. 2.84 times by 1.414. I get 4.0, and I came up with 4.5. A little bit off there, but again, I'm doing some approximations on here. I don't have the best inductors, and I do have some errors on these components, so just keep that in mind when you're doing measurements on your multimeters. So if they come close, then you know that you're really on. So how would you get really accurate answers? How would you get really accurate answers? Well, I would do is measure the ohms on this resistor, write those down, and use that in my equation. Use the meter to measure my inductor to get the exact value, and use that in my equation. And then you're going to see that things will come a little closer onto it. So I hope this explains to you some of the series parts of a RL circuit. Thank you.